Alright, welcome back to your favorite intermediate algebra course. Let's take a look at solving some exponentials, logarithmic equations, now that we're familiar with exponential functions and logarithms. Okay, so we're going to solve those, both exponential and logarithmic equations now, right? Not just simplification here. So let's look at some where you're solving by equating the exponents. Okay, if you're looking at this base, you got 27. On the other one, you got a 9. You're thinking to yourself, well, they both have in common. 27 could be written as 3 to the third, couldn't it? So there's the 27, and that's taking 27 to the 2x, right? And we know that 9 can be written as 3 squared. So I can equate those bases on those exponents. Okay? And then that 9 is taken to the x plus 2, isn't it? Okay? Now you're going to go ahead and multiply those, power of a power property. Okay, so you got 3 to the 6x. Over here you got 3 to the, and don't forget you got to distribute that because it's 2 times the quantity x plus 2, so 2x plus 4. And you say, oh, okay, if they're both base 3, then shouldn't 6x have to be equal to 2x plus 4, right? Isn't that true? Or you can say to yourself, how do I undo 3 to the x? Because you know 3 to the x looks like that. And then the inverse of 3 to the x would be log base 3 of x, right? So to undo 3 to the x, you could take log base 3 of both sides here, log base 3, because log base 3 of 3 to the 6x is 6x, and log base 3 of 3 to the 2x plus 4 is 2x plus 4. And now you can just solve that, right? Solve it as you would any old regular equation. 4x equals 4, so x equals 1, plug it back in, check it, you're okay. Okay, make sure you check for extraneous solutions here. Okay, how about if you're taking a logarithm? You know what, let me do one more like that. Similar in approach anyways. How about 4 to the 3x minus 2 equals 16 to the x. You say, can I put them as the same basis? You say, sure, 16 can be written as 4 squared, right? So in other words, there they are. So you know if they both have base 4 there, 3x minus 2 must be equal to 2x. Or you can undo it with its inverse. So take log base 4 here, log base 4 there. So now you got 3x minus 2, either way you think about that, equals the 2x. You subtract your 2x. X minus 2 equals 0. Add 2 to both sides. There it is, x equals 2. Okay. All right, now taking a logarithm of each side here. Now you obviously can't write 21 as 4 to the sum, right? Because 4 squared is 16, 4 to the third is 64, so you jump over that 21 there. So what you're going to do here is you're going to undo 4 to the x, again, with its inverse, because you know 4 to the x, you know its inverse is log base 4 of x, right? So you're going to run the inverse on each of these. Okay, so run the inverse, log base 4, because the composition on its inverse spits it out, right? Spits out the input, if you will. So you get x right here. Log base 4 to the x is x, right? Whatever's in that position. Log base 4 21 is, I don't know, so I got to punch that in, and so I better change the base here before I punch it in. Log of 21 over log of 4, which is approximately 2.196. Okay. Do another one like that. How about 7 to the x equals 46. You say, well, I can't write it as, we can't rewrite that 46 as 7 to the something, right? Because you know 7 to the 1 is just 7, 7 squared is 49, so you can't write it with base 7 there, so you undo it. So you take log base 7, both sides here. Log base 7 is 7 to the x, It's just that x. So x equals log base 7 of 46. Punch that into your calculator. Let's change it to base e this time. So ln of 46 over ln of 7, and that'll spit out 1.968. Okay, do some more here. Alright, so what if you got this 3 to the 5x minus 2 plus 2 equals 6? First you want to isolate that 3 to the 5x minus 2. So isolate that exponential. So let's subtract the 2 first. 3 to the 5x minus 2 equals 4. And now you say, well, let's run the inverse. I got to take log base what? Log base 3 to undo that 3 to the 5x minus 2. Okay, so I got to take log base 3 both sides here. And that spits out that 5x minus 2. So I got log base 3 of 4, which is some number. Now I'm going to add 2 to both sides. So I got 5x equals log base 3 of 4, that's just some number, plus 2. Now I got to divide by 5, okay? Which means I got to divide this whole thing by 5. Or in other words, take a fifth of this whole thing, right? Dividing that whole thing by 5. So x equals, I'll write this as 1/5 log base 3 of 4 plus 1/5 times 2, so 2/5. Okay, there it is in exact form, and this ends up being approximately 0.652 if you wanted to punch that in. So either of those, there's your exact form, there's your approximation on your calculator. Okay, do another one like that. About 10 to the 2x plus 1 minus 4 equals 3. So isolate that exponential, so let's add 4 both sides. 10 to the 2x plus 1 equals 7. Undo the 10 to the 2x plus 1, so what's the inverse of 10 to the x? It's log base 10 of x. So run log base 10 both sides here. So log base 10 of 10 to the 2x plus 1 is 2x plus 1. Then you got this log base 10 of 7, so the log of 7. You don't have to write base 10 if you don't want to on this one. Subtract 1 on both sides. So log base 10 of 7 minus 1. Divide by 2. So take everything, divide by 2. So I'm going to put a 1/2 in front here. So I got 1/2 log base 10 of 7 minus a half. Okay? Which is approximately negative 0.077. Let's continue on and solve some more logarithmic equations. What if we have log 7 of 3x minus 1 equals log 7 of 2x plus 2 now? Okay, so we got logarithmics here involved, okay, from the get-go. So you're thinking to yourself, well, here's the old log base 7 of x, right? What's its inverse? 7 to the x, right? So that's what you have to do here is you have to run the inverse on it. So you go 7 to that side, 7 to that whole side, because 7 to the log base 7 of 3x minus 1 is just 3x minus 1. 7 to the log base 7 of 2x plus 2 is 2x plus 2. Okay? And now you can just solve this thing as you would like usual. Add 1 to both sides. There's your 3. Make sure you plug it in and check for extraneous solutions. And the solution is x equals 3. Works out. Okay? Another one here. How about log base 3 of 2x plus 3 equals 3. Okay. So here you say, well, what's the inverse of log base 3? It's 3 to the x. So you want to run 3 to that side, 3 to that side. Okay, so log base 3 of 2x plus 3 is 2x plus 3. Over here, you just got 3 cubed, which is 27, right? So subtract 3 both sides, divide by 2, 12. Plug it in, make sure it worked in the original, and it does. You know, sometimes in a problem like this, people will think about exponentiating each side. So they'll run the old definition. They'll put the logarithmic form, you know, they'll put it into exponential form. So they'll go 3 to the third equals 2x plus 3. Remember that? You see how this one here pops out the same equation that you're solving. Okay, so whichever way you like to think about that is fine. It's called exponentiating each side. All right, let's look at checking for some. Okay, let's say we got log base 10, so log of 2x. We got log of 5x plus 15. We got equals 2. Okay. Now, when you're running this one, here's where it's going to come in handy to condense these first. You see how you got 2 logs, and you can't put 1 log on the other side because you already got a 2 over there, which is going to kind of mess things up. Because like, for instance, if you subtracted this log, 5x plus 15, you got 2 minus log 5x plus 15. You with me? That doesn't help you a whole lot here. Okay? So you want, if you're going to have logs, you want 1 on one side, 1 on the other, hopefully it's the same base, and then you can invert them. So what you're going to do here is you're going to say, well, they're both base 10. I got a plus between those. Why don't we use the old product property from last section? So I got log 2x times 5x plus 15, right? So I have the log of this whole thing here. And then, of course, I'm going to distribute that. So I got log of 10x squared plus 30x, and that equals 2, okay? Now I got it in a form where I can solve this, and notice that this is base 10, right? So I say, well, what's the inverse of log base 10? It's 10 to the x. So I go 10 to that side, 10 to that side. 10 to the log base 10 at 10x squared plus 30x is 10x squared plus 30x. Of course, 10 squared is 100. Now I'm solving a quadratic equation. So I go ahead and subtract 100 here, both sides. I got to get one side equal to 0. 10x squared plus 30x minus 100 equals 0. I notice I can take 10 out of each of these, right? Let's simplify this a little bit. And then let's go ahead and factor that. Let's see, what's that factor into? We got plus 5 minus 2. And then we're going to use that 0 product property. So x plus 5 equals 0, x minus 2 equals 0. Subtract 5 here, add 2 here. So here's our proposed answers, negative 5 and 2. That's kind of interesting. So we're thinking to ourselves, well, we better definitely check for extraneous solutions here. Is there really 2 solutions to this original equation? So let's plug in, how about that negative 5? All right, so we got log 2 times negative 5, log 5 times negative 5 plus 15, that should be equal to 2. So this is the log of negative 10. That's the log of negative 25 plus 15, negative 10 equals 2. And you're like, wait a minute, log of negative 10? The logarithmic function looks like that, doesn't it? My domain on this thing is greater than 0. I can't even have the log of a negative number, right? I can't even take that. You punch that in, it'll give you an error. So you throw it out. Negative 5 definitely does not work. You could plug in the Is our other one 2? Let's check the 2 now. So let's check 2 log 2 times 2, right? We're checking x equals 2 plus log 5 times 2 plus 15. That should be equal to 2. Move this down a little bit. So I got log of 4 plus log, and that's 10 plus 15, 25 should equal 2. And you punch in log of 4, you punch in log of 25, you add those two together. Log of 4 is, just a minute, 0.602. Log of 25, 1.398 equals 2. Check mark perfectly. And that's it. We'll see you guys in class. Make sure you bring any questions you got.